Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 8, Lesson 1, Introduction to Quadratic Functions. Before we get into the lesson today, let me remind you that you can find a worksheet and a homework assignment that go with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about those QR codes at the top of every worksheet. Those will allow you to take your smartphone or tablet, scan the code, and be brought right to the video that goes along with the lesson. All right, let's begin. So, quadratic functions take their place in terms of all the other functions we've studied. And we've seen a number of functions at this point. We've seen linear functions, we've seen exponential functions, we've even seen some sort of specialized offshoots of linears like absolute value functions and step functions. Quadratic functions, though, are any functions that can be placed in the following form. Y equals ax squared plus bx plus c. In other words, the highest power on the input variable, x if you will, is to the second. All right? Now what's important about quadratics, though, is that the a value, what's known as the leading coefficient, can't be equal to 0. And we're going to talk about why that is in a second. But it's completely okay if either the b or the c are equal to 0. Those would be what I would call the linear coefficient and the constant of the function. All right? So we're going to be playing around today with quadratic functions. We're going to be graphing them. Make sure to have your graphing calculator handy. I'll make sure I have mine. And let's dive right into it. All right. Now, this is kind of cool. The first question just simply says, read the definition above, the last one on your worksheet, and I'll put it right here. Y equals ax squared plus bx plus c. And answer the following questions. Why is it important for the leading coefficient, that would be a, all right, to be non-zero? Pause the video just for a moment and think about that. Why can't a be equal to 0? All right, well, let's just consider what would happen if a was 0. If a equaled 0, well, then that term wouldn't even be there. We would just have y equals bx plus c, and this would then be a linear function. So what makes a quadratic is that it has an x squared in it to its highest powered term. Okay? Now, let's take a look at letter B. It says circle the choices below that are quadratic functions. Okay? So there's actually more than one here. All right? But look at that carefully. Also look at this form. Remember that both b and c could be equal to 0, but obviously don't have to be. All right? And see if you can figure out which ones of those are quadratic and which aren't. All right. This can be a little bit tricky. This one's quadratic, and this one's quadratic. Both of them, by the way, lack an x to the first term. That's okay. That just means that the b, its coefficient, is equal to 0. This one's not quadratic because it's got an x cubed in it. Much too high of a power, that's eventually what we're going to call a cubic function. This one almost seems like it could be quadratic, but it's not because it involves a square root. We're going to study square root functions eventually, but they have very different properties than functions that include an x squared and an x to the first. All right? So only those two functions that I have circled are quadratic. Let's take a look at letter C. Given the quadratic function y equals 10 minus 3x squared plus 7x, write it in standard form and state the value of the leading coefficient. All right? See if you can do this for a moment. You know all that terminology, so see what you can do with it. All right, let's go through it. Standard form is this. We want to make it look like y equals some number times x squared plus some number times x plus some number. Now, to do that, what we really use is we employ the commutative property of addition. And I'm also going to change this negative or subtraction of 3x squared into addition of negative 3x squared. That will allow me to use the commutative property on this And then the commutative property on this, so we keep using that commutative property to flip-flop things. And there's our standard form, x squared x to the first and no x at all. And the leading coefficient is now -3, and that's actually quite important. It could be easy if you're looking at it in this form to think, oh yeah, there's a 3 multiplying the x squared. But the leading coefficient here is -3, okay? It's called a leading coefficient because written in standard form, it's the first coefficient you see. Okay, letter D, little function notation. If f of x is equal to 2x squared minus 3x plus 1, then find, without using your calculator, the value of f of -2. What point must lie on this quadratic's graph based on this calculation? Why don't you take a shot at this, pause the video quickly, and see if you can work out this function notation problem. All right, let's do it. As always with function notation, wherever there's an x, we're going to put in a -2. All right, remember our order of operations. We square first. -2 times -2 is +4. All right, now we'll do some multiplication. To make my life easier, I'm going to think about that as -3 times -2 to give me a +6. And then 8 plus 6 is 14 plus 1 is 15. Which means, hopefully you answered the second part, that the point -215 lies on the graph of this quadratic function. Remember, the input is the x-coordinate, the output is the y-coordinate. All right, I'm going to clear out the text, so pause the video now and write down what you need to. Okay, here it goes. Let's keep moving on. Now, whenever you're building up functions, it is sometimes helpful, or it's often helpful, to start with the simplest of all types of that function. And the simplest of all quadratic functions is the function that just simply takes the input and squares it. And what I'd like to do is actually check out and see what that graph looks like, you know? And it's pretty easy. Watch, let's do it. If I put -3 into the function, right, and I get -3 squared, well, that's -3 times -3, that's +9. And that's going to correspond to the point -3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Then if I put -2 in and square it, I'll get 4, corresponding to -2, 1, 2, 3, 4. And if I put -1 in and square it, I'll get +1, corresponding to -1, +1. If I put 0 in and square it, I'll get 0, corresponding to 0, 0, or the origin. 1 times 1 is 1, giving me the point 1, 1. 2 times 2 is 4, giving me the point 2, 4. And 3 times 3 is 9, giving me the point 3, 9. All right, I'm going to do my best to try to draw this parabola. I am terrible drawing parabolas on here. Very, very, very difficult, but as long as I can get it through all of those, it looks good, get it up there, and it's not the worst parabola I've drawn, but it's also not the best. It clearly missed this point by quite a bit. All right, so now we've got the graph, we've got the table of values. Let's talk about the range. Do you remember what the range is? The range is the set of outputs, also known as the y-values. Now, to think about the y-values, maybe we should consider about what the smallest y-value is. The minimum y-value occurs right here, and it's 0. But there is no max y-value, right? These y-values just keep going up and up and up and up and up and up. All right, so the range is y greater than or equal to 0. I have to have the equals in there, have to. Or if I wanted to do it in interval notation, remember that? I start at 0, I would stop at infinity, but I can't get the infinity, so it's got to be a parentheses. All right? So just a little preliminary work with the simplest of all quadratic functions. What we're going to do next is work with one that's a little more complicated. So pause the video now, write down anything you need to. All right, let's clear it. Okay, so all quadratic functions have graphs that are non-linear. Non-linear means graphs that are not straight lines. They curve. Ooh, that is a non-linear graph versus this, which is a linear graph. Okay? The graphs of quadratic functions are known as parabolas. Okay? And parabolas all have generally the same kind of shape. They kind of look like a hanging cable, right? That's kind of the way the one was supposed to look in our last problem. Now they can open upwards like that one, or they can open downwards like that one. They can be extremely sort of thin, if you will, and stretched upwards, or they can be kind of flat and stretched outwards. And we're going to look at how you do all of those and what controls their general shape. But the general shape of a parabola you can think of as if you were holding a chain. That's a good way to put it. Like if you had a necklace chain and you held it up. That curve is just about a parabola. Just about. Okay? So we're going to be looking at that next and some of the terminology associated with it. I'm going to clear this out. Not that there's much there, but we don't want it hanging out on the next page. And let's get into one. All right. Now I know this isn't exactly how the worksheet looks, but that's okay. We've got a parabola, y equals x squared minus 2x minus 8. And we are totally going to use our calculator to help us on this. There aren't a lot of tricks with parabolas. With lines, you need to know the y-intercept, you need to know the slope, and then you can run with it. But with parabolas, there's nothing that beats a table of values. So let's do this. Let's bring up our calculator. There it is, my favorite, the TI-84 Plus. And let's go into our y equals again. Okay, so remember it's right up here, hit y equals. Okay, clear out any equations that might be in y1, y2, y3, etc. You don't want anything in there, so clear them out. Take a moment to do that. All right, let's go up into y1. Now we need to put this function in. We're going to be careful. We're going to hit x. We can either use the squaring button or the caret button, doesn't matter. X squared minus 2x minus 8, all right? So we want to, once we've got the function in, we always want to look at it, make sure those are both subtractions and not negative signs, all right? Now, we're not going to actually ask the calculator to graph our parabola. We'll do that at other times. What we're going to ask our calculator to do is create a table of values. Now, where do we really want the table to start? That's a tough call. But look at the piece of graph paper we've been given, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The minimum x on that graph paper is negative 10. So why not make that where our table starts? So let's do that. Let's go into our table setup. It's right up here. All right, we're in our table setup. Let's make our table start at negative 10, and let's make it go by ones. All right, that's your little delta table. Make sure that's right. Table starting at negative 10, and table going by ones. All right, now let's take a look at that table. So we're going to hit second graph, right? Let's do it. Second graph. Okay. Now, if you notice, the y value at negative 10, when x is negative 10, is much too large to even fit on this graph paper. In fact, the biggest y value on this graph paper is also 10. So what we need to do is we need to go down in our table until we find a y value that fits. Okay? So go down, let's scroll down that table. Keep going, keep going. Ah, there it is, look. When x was equal to negative 3, the y value, y1, was equal to 7. So that'll fit, right? It fits. So that's where we'll actually start the table that we'll use to plot. Let's actually draw a nice table out here. I'm going to draw it horizontally so I have more space. X and y. So at negative 3, we see that y is 7. At negative 2, we see that y is 0. At -1, we see that y is -5. At 0, we see that y is -8. At 1, we see that the y is -9. At 2, the y is -8. At 3, the y is -5. At 4, the y is 0. And at 5, the y is 7. Now, I just want to pause for a minute because there's something that's really cool that's going on here, and you maybe noticed it, or maybe not. Let me switch colors. All right, notice -8, -8. Let me switch again. Go to black. -5, -5. How about another one? Green. 0, 0. Yeah, one more. We'll go to blue. 7, 7. Look at that, right? That's what's called symmetry, and it will always happen in a parabola. But let's start to graph some, okay? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Right, there's a point. -2, 0. -1, 1, 2, 3, 4, 5. 0, 6, 7, 8. 5, 6, 7, 8. 1, we're at -9. Now I can speed up a little bit. 2, we're at -8. 3, we're at -5. 4, we're at 0. And 5, we're back up there to 7. By the way, that pattern would continue. If we kept going out in the x's, we'd keep seeing those y's repeated. All right, try number 2 at drawing a parabola today. Come on, parabola. Ugh. I was doing so well there until the bottom. It's funny, on the way up, I'm better. All right, we're going to have a better graph of this on the next sheet anyway. But there it is. There's my parabola, right? It looks a lot like my last one. It's opening upwards, okay? And don't worry, both that graph and that table are going to show up on the next page. So, take a moment, but just a moment to pause the video if you need to write anything down. All right, let's do it. So there's our parabola, much better drawn when I don't have to draw it by hand. And there's our table of values, okay? So let's state the range of this function. We just did that in the last problem. Pause the video now and see if you can state the range of this function. All right, well, the smallest y value, y min, is equal to -9, and then they just go up. So the easiest way of stating the range is y is greater than or equal to -9. Or in interval notation, we start at -9, head up to infinity, including the -9, not including the infinity. Either one of these are good. That's an or thing. You don't have to have both, but it's not bad to get practice on both. Now look at letter C. Over what domain interval is the function increasing? Now this is important. Domain are the x's. In other words, I want you to tell me, over these x values, the function is getting larger. Remember increasing, decreasing? We always read the graph from left to right. So initially, actually let me stay in blue. Initially, right, the function is actually decreasing. Now the question is, when does it start to increase, right? And it starts to increase when x is 0, and it will continue to increase all the way out to infinity, right? So that's a good way to put it. Or you could say that the function, whoops, that's not 0. Why, I just keep making mistakes today. That's x equals 1, right? 1 is where we change from decreasing to increasing. So I could also say x is greater than or equal to 1. All right? Now letter D, state the coordinates of the parabola's turning point, also known as its vertex and its minimum point. Okay, so those are all terms that you need to know: turning point, vertex, and minimum point. That's easy enough. I bet you know exactly what we're talking about there. That's its turning point, and it's got coordinates of 1, -9. All right, simple enough. Now letter E. Draw the axis of symmetry of the parabola and write its equation below and on the graph. All right, so every parabola is symmetric, meaning that it looks the same on one side as it does on the other. In the parabolas that we're going to be dealing with, the axis of symmetry is always a vertical line, okay? I think I'll go green on it. In this case, the axis of symmetry is right here, all right? And its equation, because it's a vertical line, is x equals a number, specifically x equals 1. All right, and maybe I'll put some arrows on the end of it because it's a line and I don't want to get a point taken off on my standardized test. A little silly. All right, so lots and lots of terminology associated with this, and we're going to look at this problem just a little bit more, okay? But pause the video now and write down anything you need to on the screen, and then we're going to move on. All right, let's do it. Here we go, it's going to get cleared. All right. Last part of the problem. Exercise 3, right? We've got the parabola still, got the table. Letter F asks, what are the x-intercepts of the function? I'm going to switch back to blue. The x-intercepts of the function. Well, x-intercepts are where we cross the x-axis. So they're at x equals -2 and x equals 1, 2, 3, 4, right? Now, these are also known as the function's zeros. That's an important piece of terminology, the zeros of a function, all right? Why does this name make sense? As a suggestion, write out their full xy pair coordinates. So I just want to step back for a moment, pause the video, and think about why it makes sense to call the x-intercepts, not the y-intercept, but the x-intercepts the zeros of the function. All right, well, let's look up at the table. Here's x equals 2, and here's x equals 4, right? They correspond to the coordinates -2, 0, and 4, 0, right? Now, why are they called the zeros? Right? Zeros because the output is 0. So the zeros of a function, regardless of whether they're parabolas, linear, or anything else, the zeros of a function are locations where the output of the function is equal to 0. The y-coordinate is equal to 0. Okay? So I'm going to clear this out, write down anything you need to, and then we're going to move on. All right, here we go. All right, last problem. You need to be able to deal with functions in many, many different forms, including when they come in tables. Exercise 4 gives us a quadratic function, f of x, that has selected values, meaning not all the values, but selected values shown in the table below. Okay? Letter A says, what are the coordinates of the turning point? What are the coordinates of the turning point? Pause the video now and see if you can figure that out. You might want to kind of picture what this parabola looks like. All right? But we'll get there. So pause the video, see if you can figure out the coordinates of the turning point. All right. So the turning point is where the parabola changes direction. You know, in a parabola that looks like this, the turning point's down there where the y values go from decreasing to increasing. In parabolas that look like this, the turning point's right there. It's where the y-coordinate goes from increasing to decreasing, right? So take a look. Here the y-coordinate is going from 4 to 9, which is going up, 9 to 12, which is going up, 12 to 13, which is going up, and then 13 to 12 going down, 12 to 9 going down, 9 to 4 going down. So this is actually the turning point. 2, 13. This is actually a parabola. I don't want to sketch this too much. That kind of looks like this. All right, it's one that kind of goes in that direction, with this being that 2, 13 point. Now, what's the range of this quadratic function? All right, I know we haven't been given the whole function, but we kind of know that it looks a little bit like this. Now, pause the video and again, see if you can write down the range of this quadratic function. What are the outputs? All right, let's go through it. Now, it's not correct to just list all those y values. That wouldn't work. In fact, what we notice here is that instead of having a minimum y value, we have a maximum one, 13. And then it just goes down from there. So the easiest way to state the range here is y is less than or equal to 13. Or, and I think this is more challenging, with interval notation, it would look like this. Right? We're starting at 13 and then we're going all the way down to negative infinity. That's why I kind of like this one better. All right. So there's a lot of good stuff in this problem, all right, even though it's just simply a table. So pause the video now, write down anything you need to, and then we'll finish up. All right. I'm going to clear out the text. And let's conclude the lesson. So today we added one more type of function to our overall categories. We had linear, absolute value, step functions, piecewise functions, exponential functions, and now we have quadratics. And we're going to spend the entire unit looking at quadratics and talking about them because they're really cool, and there's a lot of things about them that make them stand out from linear and exponential. But we'll get into those in future lessons. For now, let me thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.